we're looking at Qwen2.5-VL, the latest vision language model from Alibaba, and it's doing things a bit differently. Instead of resizing images or chopping up videos, it processes everything at its original scale, meaning no more lost details. And when it comes to video, it tracks time using actual timestamps, making it easier to pinpoint events, even in videos that last for hours. They've also made their vision transformer more efficient with window attention, so it processes longer videos and bigger images without slowing down. Plus, with 4.1 trillion tokens of training data, it's now spotting objects with 93.6% accuracy on count bench. So, what does all this mean in practice? Better visual grounding, more accurate object detection, and sharper document parsing. Now let's dive in!
Qwen2.5-VL is a vision language model that tackles images, documents, and videos. Wondering what sets it apart? You can work with images and videos at their native resolution. No more awkward resizing or cropping that might lose important details. It also tracks time very precisely in video inputs, making it easy to pinpoint specific moments to the exact second. Another noteworthy improvement is how it identifies objects. Instead of just drawing bounding boxes, it can now point directly at the exact part of the image. That means more precision. And for documents, it can handle invoices, forms, charts, you name it, and extract structured data effectively. How does it do all this so efficiently? By using something called window attention to process large images and long videos without demanding a huge amount of computational power. You'll see 3 versions of the model. One is large for top-notch performance, and 2 smaller ones that still perform quite well but need less resources. The biggest one, Qwen2.5-VL72B, goes head-to-head with other big names, like GPT-4 or Claude 3.5 Sonnet, especially in tasks involving document and diagram understanding. The smaller ones, Qwen2.5-VL7B and Qwen2.5-VL3B, do a great job too, particularly when you consider their size. Check out the charts here. The one on the left shows how the 72B model excels at recognizing objects and parsing documents. On the right, you can see it also handles language tasks, math problems, and visual question answering, often abbreviated as VQA, at a very high level, sometimes beating models like Llama 3.170B. Overall, this isn't just a specialized system. It offers solid performance in both vision and text tasks. Now let's talk about why Qwen2.5-VL matters in the broader landscape of VLMs. Picture a sandwich, if you will. Most VLMs focus on that middle layer being generally good at various tasks. But Qwen2.5-VL puts extra emphasis on the foundation, which is fine-grained visual understanding, and on the top layer, which is multimodal reasoning that combines vision and language. Working together, these layers make the model more capable of understanding and interacting with the world. Curious about the drivers behind these advances? Recent architectural breakthroughs, better visual processing strategies, and careful data collection have pushed the field forward. More robust visual encoders, methods to scale up resolution, and larger, more diverse training sets all play a role. However, big challenges remain, like high computational costs, limited contextual grasp, and uneven performance on longer inputs. Qwen2.5-VL addresses these hurdles with 4 key tricks. First, it uses window attention in its visual encoder, speeding up processing without losing detail. Second, it uses dynamic frame sampling so it can handle videos more flexibly, adapting to fast or slow scenes. Third, it improves how it processes time by synchronizing video frames with actual timestamps. And fourth, it trains on a massive dataset, over 4 trillion tokens, improving both its visual and language capabilities. At heart, this model excels in precise document parsing, pinpoint object identification, analyzing long videos, and making stronger decisions. That means it can handle tasks like reading invoices or controlling devices, all with better accuracy and efficiency. Ready to see how Qwen2.5-VL actually processes those visual and multimodal inputs? It starts with a vision encoder built on a modified vision transformer. Instead of forcing images to a smaller size, it works with their original resolution. That preserves details that might otherwise get lost. On the video side, it uses dynamic frame sampling, slowing down when action is fast, speeding up when it's slow. Ever wonder how it lines up each video frame with its proper time? It uses a technique called multimodal rotary positional embedding, or MROP, to match each frame to its exact timestamp. After the encoder does its job, the model converts the visual features into token sequences, then hands them off to the language model decoder for interpretation. Inside the vision transformers, there are feed-forward layers, with activation functions, normalization layers to keep outputs stable, and window-based attention to reduce computational load. Images are split into patches, and the model processes them one window at a time. This helps maintain speed and efficiency. Finally, it uses a technique based on multi-layer perceptrons to merge everything smoothly before it goes into the language model. All these components work together so Qwen2.5-VL can handle big images and long videos effectively. Check out Table 1 here to compare the three Qwen2.5-VL model sizes, 3B, 7B, and 72B. They share the same vision transformer architecture, but their vision language merger and language model sections scale up as you move to larger models. That means bigger models have more layers and more attention heads, letting them tackle more complex information. They also have more output channels in the vision language merger, giving richer data flow from the images to text. Processing full-resolution images isn't simple. The number of patches can explode, which kills efficiency. To deal with that, Qwen2.5-VL employs window detention, looking at small patches at a time so things don't get computationally crazy. Only 4 layers do full attention over the entire image, while the rest focus on 8x8 patches of 112 by 112 pixels. This smart approach preserves details without resizing. For video, the model groups 2 consecutive frames together to cut down on the tokens fed into the language model. It also uses positional encodings in both 2D and 3D to help it keep track of where patches appear over space and time. Various normalization layers and efficient activation functions ensure everything runs smoothly. The upshot? Qwen2.5-VL can handle large images and lengthy videos without breaking a sweat. Now, let's see how Qwen2.5-VL processes these different visual inputs in more detail. On the spatial side, it turns images of varying sizes into token sequences that reflect their real dimensions. Older models might have resized or normalized images, but this one keeps each image at its original scale. That helps it preserve spatial clues like object location and shape. With videos, dynamic frame sampling is a game changer. It can choose more frames when there's a lot of motion and fewer when the scene is calmer. Wondering how it keeps the timing consistent without adding more compute? Instead of stacking extra layers, it aligns its internal time markers with real timestamps. That way, it knows how fast events are unfolding. Let's talk about positional embeddings. These guide the model on where parts of the input appear in space or time. For videos, Qwen2.5-VL splits the embedding into 3 parts for time, height, and width. Unlike older methods that assigned positions purely based on frame counts, this approach attaches the actual timestamp to each frame. That means timing remains accurate, even if the frame rate changes. Training data also got a boost. Compared to earlier versions, the dataset has grown to about 4 trillion tokens. That includes image captions, OCR results, and video descriptions. Plus, there's a focus on interleaved image text data, which shows both images and text together. This helps the model build stronger links between visual and language cues, keep context, and handle cases where one modality might be missing. So how does Qwen2.5-VL make sure all that training data is top quality? They start by cleaning raw data, then scouring it for how well the text and images line up. This filters out noise and ensures the model sees data where images and text truly complement each other. Better data means better reasoning. For object grounding, teaching the model to recognize specific objects, Qwen2.5-VL uses native resolution coordinates, so everything stays true to real-world sizes. The dataset for that includes more than 10,000 categories, spanning common items to rarer ones. Synthetic data adds even more variety. For tasks that ask the model to find multiple instances of the same object, there's extra training material to help it handle those tricky scenarios. Pointing tasks require even more precision, so they combined public datasets with synthetic ones generated by automation tools. And for document parsing, they put together a huge dataset of documents in HTML format. Why HTML? It preserves layout, text, charts, and illustrations all in one place, making it easier for the model to figure out the structure. All of these data collection methods help Qwen2.5-VL learn to parse complex documents naturally. Let's look at how Qwen2.5-VL puts these diverse inputs together to sharpen its skills. First, check out the example of HTML formatted documents here. Each element, paragraphs, tables, charts, or formulas, appears with HTML tags and bounding boxes marking its location. This structure helps the model keep track of how different pieces of a document relate to each other, which is especially useful for complex layouts. Next is OCR data. OCR stands for Optical Character Recognition, and it's what allows the model to read text from images. The OCR dataset covers multiple languages, such as French, German, Spanish, and Japanese. They also created 1 million chart images using tools like Matplotlib and Plotly. Why so many charts? Because the model needs to learn how to handle different types bar charts, heat maps, and more. Table data is also in the mix, with 6 million real-world tables that were carefully curated. Videos get a special treatment too. The model uses dynamic frame sampling, which we talked about earlier. Longer videos, over 30 minutes, are summarized with multi-frame captions to help the model grasp key moments without getting bogged down. Finally, for decision-making tasks, they included screenshots from mobile, web, and desktop platforms. Each screenshot has captions describing the interface, along with annotations pointing out various UI elements. This variety helps the model not only see what's on screen, but also understand how people might interact with it. Here's how the training itself unfolds. It happens in 3 phases that gradually build up Qwen2.5-VL's multimodal skills. First is visual pre-training. Only the vision transformer part is trained here, using about 1.5 trillion tokens. That includes image captions, visual knowledge, and OCR data. Why so many tokens? More data helps the model grasp patterns in images, texts, and the relationships between them. The sequence length is capped at 8,192 tokens, a sweet spot for both detail and efficiency. Then comes multimodal pre-training, where the model's visual and language components learn to work together. This phase uses a massive 2 trillion tokens and introduces tasks like visual question answering, VQA, video understanding, and text-image alignment. The model gets better at connecting what it sees with what it reads, still keeping that 8,192 token limit to ensure stable training. Finally, there's long context pre-training. This extends the model's ability to handle sequences all the way up to 32,768 tokens. That's crucial for tasks that involve long documents or extended videos. They used 0.6 trillion tokens for this phase, packing data samples dynamically to keep GPU usage balanced. By the end, Qwen2.5-VL emerges with the ability to handle complex inputs and do it quickly. Let's talk about supervised fine-tuning, or SFT. This is where Qwen2.5-VL learns to follow instructions better for both text and multimodal tasks. The dataset here has about 2 million entries, evenly split between text-only and multimodal. Because multimodal entries contain not just text but also visual tokens, they're heavier on computation. The data covers mostly Chinese and English, with some multilingual examples to broaden language coverage. They varied the conversation styles. Some are single-turn interactions, others have multiple turns or multiple images. Sources include public repositories, curated collections, and search queries, giving the model exposure to real-world prompts. These examples also include specialized tasks, such as visual question answering, coding, math, security, document recognition, and video tasks. That variety ensures the model can handle a wide range of scenarios. Data quality is a priority, so there's a 2-stage filtering pipeline. First, a model called Qwen2.5-VL Instag tags the data into 8 major categories, each with about 30 subcategories. For instance, in the coding domain, you'll see subcategories like debugging, code generation, translation, and code understanding. Next comes domain-tailored filtering. This step removes poor quality data from both public and synthetic sources. The result? A cleaner dataset that leads to sharper performance. So how do they ensure the final dataset is top-notch? First, there's rule-based filtering. They define clear rules to weed out low-quality examples, such as repetitive OCR outputs or incomplete synthetic answers. This makes sure Qwen2.5-VL doesn't learn from misleading data. Then they do model-based filtering, where earlier versions of the Qwen2.5-VL family double-check the complexity and relevance of responses. Only the data that's accurate, helpful, and visually well-grounded gets a pass. Rejection sampling is also used, especially for tasks that require tricky reasoning, things like math, coding, or domain-specific visual questions. They rely on ground truth answers to keep only the correct samples, tossing out responses that miss the mark, or switch languages mid-response. One tough challenge is making sure visual and textual reasoning align properly. Sometimes a model might interpret an image incorrectly halfway through its reasoning steps. To fix that, they apply both rule-based and model-based checks at each step. That way, the final dataset emphasizes proper interpretation of visual details. By combining all these filtering methods, Qwen2.5-VL ends up with a curated set of high-quality examples that really tests and teaches its understanding. Now, let's see how Qwen2.5-VL stacks up against other cutting-edge models. Check out this table of results across different tasks, like college-level problems, math, and VQA. For college-level tasks, Qwen2.5-VL landed a score of 70.2, beating many open-source models, and even coming close to GPT-4. On a more advanced reasoning benchmark called MMMP Pro, it got 51.1, holding its own among the top closed-source systems. In math tests, Qwen2.5-VL did really well, with a 74.8 on MathVista, above the previous open-source record of 72.3. On MathVision, which mixes visual interpretation with math, it scored 38.1, showing strong cross-modal reasoning. For VQA, it achieved 88.6 on MMBench-EN, nudging out the former best of 88.3. On MuirBench, it scored 70.7, and on BLI-INK, 64.4. Multilingual capability? It got 31.7 on MTVQA. In subjective evaluations such as MMWet and MMTbench, it scored 76.2 and 7.6, indicating solid conversational performance and user satisfaction. Interestingly, it also delivers well on pure text tasks. That versatility is part of what makes Qwen2.5-VL stand out. You might wonder how it holds up when the focus shifts to text-based challenges. In general tasks like MMLU Pro, which has multiple choice questions across many subjects, Qwen2.5-VL 72B scored 71.2, a top-tier performance. It jumped even higher to 85.9 on MMLU Redux, a tougher version of that benchmark. For LIVEBENCH0831, it got 57.0, which is decent, but leaves a little space for further improvement. If we look at math and science tasks, Qwen2.5-VL 72B scored an impressive 95.3 on GSM-8K, grade school math. However, it scored 49.0 on GPQA, which tests general physics and math knowledge, so that's a bit lower. On math, it notched 83.0, showing strong complex problem solving. For coding tasks, Qwen2.5-VL 72B logged 87.8 on human evil and 79.5 on multi-PLE, which checks code generation in various programming languages. These results demonstrate solid programming skills. In alignment tests like IF-eval, Qwen2.5-VL 72B scored 86.3, outdoing many models, suggesting it can produce answers that users find logical and context-appropriate. All in all, it's balanced across math, coding, alignment, and more. Now let's move on to document and chart comprehension. Curious about OCR performance? On CCOCR, Qwen2.5-VL 72B scored 79.8, outperforming every other model tested. For OmniDocBench, which spans English and Chinese document understanding, it led the pack with 0.409 in English and 0.543 in Chinese. Impressive multilingual strength. What about visual elements like charts and infographics? Look at AI2D results, 88.7, showing a strong grasp of diagram relationships. For Chart QA, which involves answering questions from chart data, Qwen2.5-VL 72B got 89.5, confirming it can really dig into visual data. Over in VCR, or Visual Common Sense Reasoning, it achieved 80.5, indicating solid logical reasoning with both images and text. Finally, on OCR Bench, _V2 a suite that combines parsing and deeper visual comprehension. Qwen2.5-VL 72B grabbed 61.5 in English and 63.7 in Chinese. These are top marks compared to other leading models, so if you need robust document analysis or chart interpretation, Qwen2.5-VL has you covered. Let's check out Qwen2.5-VL's performance in grounding, counting, and video tasks. For object grounding, you can see the Ref Coco results 92.7 on the validation set. That's top tier. OD in W, which tests open vocabulary detection, shows 43.1, meaning it can detect a lot of objects not explicitly in its training categories. And for point grounding, it scored 67.5, which proves it can pinpoint specific details accurately. Counting tasks? Take a look at CountBench. Qwen2.5-VL 72B scores 93.6, well ahead of others. This means it's pretty good at figuring out how many objects are in a scene, even when it's complex. On the video side, check out Bench-Video. The model got 2.02, showing better narrative understanding in videos. For MV Bench, which tests multi-view reasoning, it led with 70.4, and in tasks like charades STA, a video grounding benchmark where you find specific actions at exact timestamps. Qwen2.5-VL 72B scored 50.9, even beating GPT-4o. Impressive, right? That's state-of-the-art in locating and interpreting events in video. Finally, let's talk about Qwen2.5-VL 72B as a GUI agent, someone who can navigate and control graphical user interfaces. On ScreenSpot, which tests visual interface recognition, it scored 87.1%, keeping pace with Gemini 2.0 and Claude. But in the trickier ScreenSpot Pro, it jumped to 43.6%, blowing past Aguvis 72B's 23.6%. Moving to Android World benchmarks, which focus on phone-based tasks, Qwen2.5-VL 72B hit 93.7% on Android Control Low M. That's almost perfect in operating device functions. And it reached 35% on Android World JS, better than the 7B version. On Mobile MiniWol B++ SR, a complex multi-step environment, it led with 68%. That indicates strong reasoning and adaptability in sequential tasks. For desktop-style benchmarks, like OS World, it got 8.83%, beating its smaller sibling but still leaving some headroom compared to other models like Claude. Overall, it's a versatile digital assistant, skilled in both visual recognition and task execution across different platforms. Thanks for joining us today. Happy learning and stretching together.